Professor R.P. Singh is a faculty member in the Atomic, Molecular and Optical Physics Division at Physical Research Laboratory, Ahmedabad. He has published over 1,000 research articles and conference papers with Google Scholar H index of 27, item index of 83, and citations of 3,687. His areas of research include light scattering, phase singularities of light, nonlinear optics, and quantum information. Presently, he is engaged in experiments on high-dimensional entangled states, free-space quantum communication, quantum imaging, and quantum radar. On behalf of all the RIOS members, I welcome you, Professor, to this webinar. Now, I kindly request Professor R.P. Singh to begin the presentation.
So, the topic is experiments in free space, quantum key distribution. So, why free space and what is quantum key distribution? So, quantum key distribution is basically a like application of quantum communication. Okay, and why free space? We are going for free space quantum key distribution because optical fibers which are used for communication and also for quantum communication, they have certain degree of attenuation, and you can't use for long range quantum communication. So if you want to have long distance quantum communication and quantum key distribution, you have to have a free space. Okay, you can use satellites or free space as such. So these are the students and young faculty members, Rupesh, Gautam, Sashi, who have contributed to the work. And you can see that I am at Atomic, Molecular and Optical Physics Division at PRL. We have initiated Quantum Science and Technology program at PRL, covering all the verticals of quantum science and technology. Okay, that includes quantum communication, quantum computing, quantum sensing and metrology, attosecond physics, quantum control of wave packet. So we cover almost all the verticals of quantum science and technology. And you might be aware that India has launched a national quantum mission. So government is also giving a lot of like emphasis on quantum science and technology. And just a little bit introduction about Physical Research Laboratory. Some of you may not be aware that Physical Research Laboratory is now 75 years old. Celebrated this Platinum Jubilee. And it's the parent institute for ISRO. Everybody knows ISRO, Chandrayaan 3, everybody knows. And Aditya L1, all those missions, ISRO. So its parent organization, all the space-related activities in India started from Physical Research Laboratory. ISRO came out of PRL only. Okay. So it's quite an old institute. We have different branches of research in PRL. This is just one of the branches, Atomic, Molecular and Optical Physics. We have astronomy, astrophysics, planetary sciences. Then we have theoretical physics. We have the space and atmospheric sciences. We have solar physics. So we have a lot of like experimental activity going on in our institute along with theory. So why one goes for quantum communication? As I told you, quantum key distribution is just an application of quantum communication. Quantum communication is more general. What do you mean by quantum communication? When you communicate through quantum states, okay, or when you use quantum mechanical principles for communication. So that is quantum communication. And so if you're using quantum states, like basic unit is qubit for information in quantum mechanics. So you use qubits instead of bits that you use in classical communication. And then you use qubits. Certainly qubits are quantum states. Okay, so they follow the laws of quantum mechanics. And what is the need of quantum key distribution? Basically, when you are distributing keys, okay, and that has to be secured. Okay, distribution. of the key has to be secured. And present day, this key distribution or key generation a mechanism that may become vulnerable, that may not remain secure once we get quantum computer, because there are quantum algorithms. I will not get into more detail about quantum algorithms, because quantum algorithms are available which can break the present day encryption. Okay? uh, if they are like implemented on quantum computer, this quantum algorithm. So all our present day encryption scheme becomes like vulnerable, and our messages, secret messages or confidential messages will not be secure enough. Okay. So that is the problem. So basically this quantum key distribution or secure quantum communication, that comes into the response of quantum computer, emergence of quantum computer. Okay. And why like everybody wants to have this secure quantum communication or quantum key distribution? Um, because suppose somebody is tapping your information, and once they have quantum computer, they can break the key, they can get the key using quantum computers, and they can decrypt your information later. You can keep on storing the message. You can tap the wire and keep on storing the message, and later on you can decrypt the message. So that is a very serious problem when for strategic communication. And one thing also I would like to point out, that your message, like still there is encryption is there. So what is the problem? We are having encrypted message that's secure enough. Um, So, as I told, later on, they can be like broken. This encryption scheme can be broken. You can have information about key. So, your message is as secure as your key. Okay. So, because key can be vulnerable later on, so you have to find out a way so that your generation and distribution mechanism of key, that is secure enough even against quantum computer, even against attack by quantum computer. Okay. So this quantum mechanics provides a way to generate and distribute the key. That is called quantum key distribution. So once you have like secure key, you can encrypt your message with that key, and then your message will secure. So your message is as secure as your key, and quantum mechanics provide a way to generate and distribute key that is secure enough. So that's what I told. One can intercept now and decrypt later. That is really very serious for a health sector, strategic defense, and strategic communication. And second thing, one should always keep in mind that when you are communicating through quantum states, you can't amplify. You can't use same devices, amplifiers, routers, transceivers, as you use in classical communication, a present day traditional communication, because that will spoil the state. Okay, quantum state, to be precise. So how to go about this quantum key distribution, which is example or application of quantum communication. So one requires single photon source or entangled photon source, because like communication, present day communication, it's being used like light, it's through light or photons. Okay, so even quantum communication we use photons only, but instead of like electromagnetic wave, we talk in terms of quantized field or photons. Okay, or entangled photons, which are very basic to the quantum mechanics. So we can use physical variables like polarization, momentum, frequency, time information, a time bin, uh, to characterize a quantum state for encoding and encrypting the information. Okay. So all those variables can be used for encoding quantum state and encrypting the information. And as I told already, it can be communicated to free space or fiber because we are dealing with photons or light. And I have indicated that because fiber one can't use for long distances because they have certain degree of attenuation. So we have to go for free space or satellite-based quantum communication. And free space quantum communication assumes importance because this is the stepping stone for satellite-based quantum key distribution or satellite-based quantum communication. One can have quantum key distribution, QKDs for quantum key distribution, okay, using discrete variables as well as continuous variables. When I say discrete variables, I mean there are like polarization is one example, orbital angular momentum is another example, time bin or time information, time distance is another example. When I say continuous variable, you have to use field quadratures, quantized fields, okay? That's a quantized field you have to consider. So both ways you can use continuous variable, that is called CBQKD or DVQKD, discrete variable QKD, and there are number of protocols in both categories, CBQKD and DVQKD. You have prepare and measure and entanglement based. Okay, and prepare and measure, there are protocols like BB84, B92. There are many other protocols. These are the two very popular protocols. One is decoy state BB84 or just decoy state protocol. Then we have entanglement-based, entangled photon-based protocol, BBM92 or ECAT91. Okay. Same way in continuous variable, we have protocols like prepare and measure as well as entanglement-based. When we talk of this continuous variable or field quadratures, when in entanglement-based, we use squeeze states, and for prepare and measure, we use like Gaussian modulation-based or discrete modulation-based. And this is GG02 is one of the protocols, okay, name of the scientist, initial letters of the scientists, and given in 2002. And this quadrature phase shift keying, QPSK is for quadrature phase shift keying and quadrature amplitude modulation scheme under continuous variable quantum distribution protocol. As I told you, this free space quantum communication is the stepping stone for satellite-based quantum key distribution, so that we can cover long distances, which is not possible through fiber. And ultimately, one has to like integrate free space or satellite-based quantum key distribution with fiber. So both are important. I don't say just satellite-based can do all the job, or fiber will do the complete. Fiber will be the best thing for quantum communication. Both have to supplement each other. Both are supplement and complement each other. So as I told, one can use single photon source or weak coherent pulse. Or weak coherent pulse, you should keep in mind, weak coherent pulse is not single photon source. So one can use single photon source or weak coherent pulse as well as entangled photon source or quantum key distribution or quantum communication. When we use entangled photon source, this is satellite, okay, and entangled photon source is sitting here. So entangled photons are generated in pairs. So one of the photons comes here, you can say Bangalore, another photon goes to Ahmedabad, and you measure the properties, okay. You encode in terms of polarization, whatever variable you choose. You encode your photons using that information, and then you measure and get the key. Okay, measure two distances, these two places, and you get the key. So you need this when you are sending photons encoded in polarization. Okay, this is quantum channel because quantum states were sending, and this is classical channel that is also very much required. You can use Ethernet, phone line, whatever you choose. So this is also required because after sending these photons, after measuring after measuring the variables, in this case it's polarization, they talk among each other, these two parties. Generally, traditionally they are called Alice and Bob. So they talk to each other, which kind of measurement they have made, and accordingly they derive the key. I will discuss more as we go further. So here, key is not stored in satellite. Okay, just entangled photon source is sitting here, and key is being generated here at two places. So this is called untrusted node because key is not being stored. So you need not to trust the satellite. Okay, key satellite will leak the information to somebody, some other satellite or some other place. So this is untrusted node. Okay, but here there is another scheme, as I told, prepare and measure. This is entangled photon based, and this is prepare and measure. Here, satellite there is device which prepares the quantum state. Okay, we can't pass, and then it sends to station A, and both will have key now KA, suppose station A, and then satellite goes to another station B and distributes the key KB. Okay, so now satellite is having both the keys K and KB. So you do the exclusive R, XOR operation, and then you have satellite. There is device one can do this XOR operation, and then this KB that can be sent, and another XOR operation will generate the K. So now both the stations are having K, and one can have secure communication. So this is prepare and measure, and this is entangled photon paste. Okay, but here, because as told you, satellite is having both the keys, okay, K and KB. It's being stored there. So this is called trusted node. You have to trust the satellite that it's not leaking the key. Okay, it's not passing on the key to some other place. So this is called trusted node. Here satellite is acting as a trusted. Let's go further. So how you get the security of QKD? Basically, it comes because we are using mutually unbiased basis. This is very important in quantum key distribution. One has to use mutually unbiased basis. So here you see when you talk of polarization, you have three mutually unbiased bases because polarization is two-state basis. Okay, so you have three mutually unbiased bases. Here we are using two mutually unbiased bases, that is rectilinear and diagonal. Then rectilinear, you have H and V, horizontal and vertical, and when it's diagonal, it's diagonal and anti-diagonal. So if you have prepared a state as diagonal, okay, diagonal polarization, your proton is in diagonal polarization, and you choose the basis rectilinear, you measure in HV basis, sometimes half of the time you will get H, and half the time you will get random results, sometimes S, sometimes V, and both have equal probability. So you can't make out what is the state. You can't have information about the state which you have prepared. Same way, if you have prepared the state in horizontal polarization and choose this basis, this DA basis, you can't have information about the state. Randomly, you will get results DRA. Okay. So that's the beauty of mutually unbiased basis. That's what you select for making the key or distributing the key, generating and distributing the key. And then no cloning theorem, that is very important. You can't clone, you can't make a copy of the arbitrary quantum state. Quantum mechanics does not allow to make a copy of an unknown state or arbitrary state. And another thing which you should remember when I was talking of this mutually unbiased basis, uncertainty principle also plays a role. Okay, just think of it, how uncertainty principle plays a role when you select this DA and HV basis. Okay, and how it helps to make it secure. You have to think on your own. So uncertainty principle, which is very basic to quantum mechanics, all of you must have read about it. That also plays a role making it secure. And third thing, which is you can always put a threshold on the error which is not there in traditional classical communication. This EB is error rate, yeah, quantum bit error rate you call. And for BB84 protocol or BBM92 protocol, it is 11%. And this is binary Shannon entropy, S2, okay? And these are the random variables, X, okay? So if you calculate, suppose if this for BB84, this Cuber threshold is 11%, okay? Means if there is rate, error rate goes beyond 11%, you can't generate the secure key. So that is the threshold you can put on the error, okay, which is not there in classical. So 11% if you put, R will become 0. You can't generate the secure key. So let's discuss one of the way, like first protocol which was given for quantum key distribution, BB84 protocol, and it's basically Bennett and Brassard, and given in 1984. And first time it was presented in a conference at IIC Bangalore. Okay. So here, what like Alice, it's a prepare and measure protocol. So Alice prepares randomly this quantum state, random population states, okay, and then sends to Bob, okay, and Bob selects randomly this basis, these two bases, okay, like linear and diagonal anti-diagonal basis, or horizontal vertical and diagonal anti-diagonal basis. So if both select the same basis, like preparation and measurement, if they are having the same basis state, you get the key, and that is called shifted key. So you can see here, if LS is sending, you can assign bit value to the population state here. All those four population state, you can assign a bit value. Like you can assign 0, and A you can assign 1. Similarly, V vertical you can assign 1, horizontal you can assign 0. So you see, Alice sends this diagonal thing, and Bob measures in horizontal vertical basis. Okay, so this doesn't form a key. But if Alice is sending D and Bob measures in this DA basis, diagonal basis, you get the key. So that's how you generate the key. Same way you can see here. This is the vertical V. Alice is sending and Bob is selecting HV basis. Okay, so you get the key. So this is called shifted key. Once you have shifted key, like this is the quantum mechanical principles involved in this generation and distribution. After that, you follow the classical protocols of classical communication protocols of error correction and privacy amplification, and you get a secure key. Okay, that's what. And then once you have secure key, you can encrypt your message and send it, and other party can decrypt. And one should keep in mind that this quantum key distribution is symmetric key distribution, means both the parties are having the same key. So how you implement these quantum key distribution protocols? You need to have source, and you need to have detectors, and of course you need a lot of optics for transmission and collection, and there are many other optics. As we go along, you will see that. Okay, so you can use two kind of sources, weak coherent pulses or entangled photons or single photons, both you can use. So weak coherent pulses, how you make these weak coherent pulses? These are pulse lasers, and you attenuate in such a way that each pulse, on average, each pulse will have less than 1 photon. Okay. So you attenuate your pulse laser in such a way that you will have less than 1 photon per pulse. So that is called weak coherent pulse. Okay. But this is not single photon source. Okay. We'll discuss much more later. So, and then entangled photon source and single photon source, they are made using nonlinear crystal. Most of the time we use Chi2, second order nonlinear crystal. This laser is pumped, okay, to the nonlinear crystal, and one photon from this pump laser. Here we are using blue 405 nanometer, is converted into two photons, and this is called spontaneous parametric down conversion. Okay, parametric down conversion. Um, because its energy, you see, this is red, so energy is lower, so that's by down conversion. So one photon of blue, you get two photons of red, and since these two photons are coming in pairs, okay, if you measure one, it tells you that another photon is there because they are in pairs. So presence of one heralds the presence of another photon. So that's why it's called heralded single photon source. And if you measure like polarization, if you can see that polarization correlation, if you measure between these two photons, so you can, if they are strongly correlated, we will see when we call them as entangled photons. So you measure polarization correlation, and if they are very strongly correlated in polarization, you say they are entangled. Okay, in polarization. Okay? So whatever variable you measure, you say entangled in that variable. You can't talk of another variable. And then for transmission, this is photon or light. So you can use optical fiber or free space. Then you have to have detectors. You can use avalanche APDs, avalanche photodiodes, based single photon detectors. Okay, they are very compact and are not very expensive. Or you can use superconducting nanowire single photon detectors. Okay. Svetlana is there. So Russia is pioneer of this SNSPDs. Okay, first time it was developed in Russia. Now it is like being like China, US, all the countries are making these SNSPDs. But they use, like, because superconducting, they use cryostat, and they are quite bulky and costlier also, quite costly compared to avalanche photodiode based single photon detectors. So you have both the options. Okay. So we talked about this BB84 protocol, or prepare and measure protocol. So here, as I told, you are using weak coherent pulses. So you are attenuating the laser, and laser follows Poissonian distribution, like photon distribution in laser follows Poissonian distribution. Because of that Poissonian distribution, some of the pulses may have two photons or three photons. Okay. So in Eve or hacker, Eve can collect those two photons, and one photon it can measure, one photon it can pass. Okay. And that way, and when they do this classical communication for reconciliation, or telling the basis to each other, what basis they have selected, you can have information about the key. So that is called photon number splitting attack. So this is very serious attack. So you can't use like very high mean photon number per pulse, and then you get very low key rate. Okay, because as you increase the mean photon number per pulse, probability of getting more than one photon per pulse increases. So what happened? Decoy protocol was proposed. In this, you send some extra pulses, monitor to channel whether Eve is there or not. Okay, so that's called decoy state BB84 protocol. Some people call just decoy state. So you send extra pulses to monitor the channel if there is Eve. Okay, that's the thing in decoy state protocol. So then you can use like higher photon number per pulse, and you can increase the key rate. So how do you do these things like quantum key distribution? You have to have like a random generation of polarization state, Okay, this four population is randomly generated. So the random number generation is done by this driving electronics, and then you have to have a time tagger, precise time information, what when you are sending and when it is being received. So both ends you have to have very precise time information. Okay. So as I told you, when you are sending this quantum state from one place to another, that's called one particle and that's called a quantum channel. And then you have to have this classical channel also. Okay, for basis reconciliation, error correction, and all those things. Okay. So you will see you require a lot of optics. All the optics is not here. You require even more optics here. It's just the indicative optics. So you have lasers, then you have half wave plates, you have polarizing beam splitter. Polarizing beam splitter, what it does, like it transmits the horizontal polarization and reflects the vertical polarization. So this laser, this combination of half wave plate and PBS, that's used for this attenuation. Okay, you can attenuate given laser pulse using combination of polarizing beam splitter and half wave plate. And this driving electronics is randomly switching on these lasers, randomly switching on, just important, randomly switching on these lasers. And then you have like here half a plate, so that generates like h is coming, so that will convert it. You are using half a plate 45 degree, that will convert it into d, and v is coming, that will convert it into a. Okay, so that's what, so you are generating here d and a, and here this is pbs, just polarizing filter, so you are generating h and v. So this is the four polarization states. They are being combined. Okay, all are coming. So you can't discriminate. And then it's being transmitted to or directed to bomb. Okay, that's what we are doing. Then this is launched through optics. You have collection launching optics. Okay, and then you have collection optics at LSN. This is for free space. If you want to have fiber, you just connect, like after this preparation, you can connect through fiber, and then you can take it to the another party bomb and you can measure there. This is free space, so you are using optics. Okay, launching optics. Then you are having like reference laser or beacon laser, it is called, to align, like, so that you can get, it is called pointing and tracking. Okay, so laser, so so that you can get maximum signal. And here you measure all these four polarization states. Okay, here you see PBS again. So these two state, these two detectors, they measure H and V, and here half a plate is there. So these two detectors measure D and A, and then you have to have this time information. Okay, time synchronization and time stamping. So one can do it in the lab, okay, lab environment, but to be practical, one has to go out and do it in the field. So we have done in the field also after doing it in the lab. So you prepare your collect all your optics on a breadboard, okay, and then like a source part as well as the detection part, Ellis and Bob, prepare and measure, Ellis and Bob. We prepare on an optical breadboard, and then we take it to the terrace of our building. So that's Sarika doing experiments here. And now she is in Fraunhofer Institute, Germany, working on quantum redistribution. Okay, again. So that's what our arrangement. It shows schematic diagram. Here this is a Ellis box, and because we have only two buildings in our campus which can be used for this quantum redistribution, they are 100-meter apart. So to make it 200 meters, this non-line, this is called non-line of sight. Okay, quantum key distribution. It's not exactly in line of sight. Okay, because you are reflecting here. So, but it makes like 200 meters quantum key distribution. Our main purpose is to make it 200 meters, slightly longer. And this is receiver. One cabin is for transmitter, Alice. So these two breadboards are kept here. And this is reflector, another building. So as I told, time stamps thing is very important. Time records are very important. So suppose H state you are transmitting, Alice is transmitting, and Bob is measuring H. Okay. So this is 200 meters. So it comes around 689 nanosecond. Okay. So you get this H thing, maxima at H. Suppose you change the delay as 690 nanosecond, you will not get this maxima. Or if you select 688, you will not get this maxima. So that's what this is. Time stamping is very important. Depending on distance, you will have to use different delay. And then you see we are getting very less. Okay, at the same delay. Delay is same for you are sending H. And just to verify that your setup is fine, you send H and then measure D and A. So if you are sending H, D and A should be almost equal numbers. So you see here, D is coming around 225, 230, something like that, at same delay, 639 a second. And A is also coming around 30, 40, something like that. So they both are equal almost. So you know that your setup is fine, and whatever you measure, you will get the right key by measuring the pollution states. So that's what you get. This key you get. Okay. Like transmitted number of pulses, then detected, then shift. After shifting, you get this much. Then error bit you can calculate, and then quantum bit error rate. So very less. Error like threshold for BB84 is 11%, but you can see that we have quite less this quantum bit error rate. Okay, and that gives like 200 kilobits per second. You can go for higher. There is why you are getting 200 kbps, because we are using indigenously developed diode laser. Our driving circuit, current driving circuit, controller, diode laser controller was in-house developed. That was like 5 megahertz rep rate. That's why we are getting 200 kbps. If you increase the rep rate or repetition rate of laser, pulse laser, to gigahertz, you will get much higher. Okay, just limitation like when we are doing experiment, we had laser that was having repetition rate of 5 megahertz. That's why it's. So you can, when you talk of theory, everything is ideal, and your quantum key distribution provides information, theoretically secure communication. But in practice, your source is not ideal, your detector is not ideal, and there may be information leakage, or you can say this shortcomings in the source or deficiencies in the source from the ideal, which you assume in theory, that may lead to side channel attacks. So we have studied source side channel attack as well as detector side. Here, just source side channel attack I'm showing you. So source may have like we are using 4 diode lasers here, so they may have slightly different wavelength. They may have slightly different pulse width because we are using pulse lasers. They may have different like polarizations also different from like what we intend to make. So all those things are there, and then we using cross correlation between these two lasers, okay, for particular variable, we can find out the mutual information between Alice and Eve. So information leakage to Eve, or Eve is like eavesdropper or hacker, whatever you say. So that can be calculated using mutual information. So instead of Bob, it is Alice to Eve, which will remember the Alice to Eve, eavesdropper. And that using cross correlation between two signals at zero lag. This is the cross correlation. And if it is delta S is equal to 0, you can calculate this integral. If R delta S is equal to 0, this R is 1, at this means they are indistinguishable. And if they are indistinguishable, all these diode lasers are, suppose all these lasers are indistinguishable in wavelength, so R will become 1, and this mutual information between Alice and E will become 0. So because of wavelength, there is no information leakage if all are exactly same wavelength, but generally in practice, it will not be 1 and there will be information leakage. So same way you can like pulse width also you can do, all those things you can do, and you can keep on changing. Like for wavelength, you will have optical spectrometer. Then for pulse width, you can have like photo detector and oscilloscope. So you can keep on changing the instrument here for measuring different variables. Okay? And you can calculate this mutual information between Alice and you, and you can find out what is the information leakage. So that's what we have calculated for differences in wavelength. It can be 10 power minus 3 bits per pulse. So suppose you are generating gigahertz rate, suppose 10 power 9. So you can calculate like quite a good number of bits you are leaking. Same way for pulse width, it may be 10 power minus 3 bits per pulse. For arrival time differences, you can have 10 power minus 3 bits per pulse. So this kind of information leakage you will have. And when you do this error correction and privacy amplification, you have to, in privacy amplification particularly, you have to take into account these factors of what kind of information leakage is there due to start coming in your system. So information leakage can be there for spatial mode also, pixel mismatch. Okay, and it may be there because of correlation error also. All those things you can calculate. Okay, using cross correlation and mutual information between Alice and you. So this is regarding practical problems. Instead of ideal, you will have information leakage, and then you have to take into account those information leakage. Then, as I told, this weak coherent pulse, and we are limited to single photons, okay, or when there is only one photon per pulse. But in general, when we are using weak coherent pulse, there may be 2 photons or 3 photons. So instead of discarding those pulses which are having 2 photons or 3 photons, we can use them and to increase the key rate, okay. What we do, we use the coincidence detection. Coincidence detection we use, and we measure 2-fold and 3-fold coincidences. And coincidence measurement is at the heart of quantum mechanical measurement. And using that coincidence detection, we can increase the key rate because we are not discarding these 2 photon pulses or 3 photon pulses. So that's what we have done. So when you are having these 2 photon pulses, these are the possibilities. 2 photon may be transmitted, 0 photon may be reflected. Probability is 1/4. The 1/2 probability, 0 photon transmitted, 2 photon, so 1/4. So these are the possibilities. When you have 3 photon pulse, so these are the possibilities, the probabilities. Okay, 3 photons may be transmitted, 0 reflected, so 1/8. Same way 1 and 2, 3/8. All those things you can calculate. And this is the basically Poissonian distribution. It says for different photons, like there is probability for 2 photon, 3 photon. You can see that. Okay. So this you calculate coincidence measurements, experimental coincidences. You can calculate. This is like a Y2. This is called yield, and this is like for mu, like mean photon number per pulse, per given mu, mean photon number per pulse. This is the P2, like 2 photon per pulse, probability of getting 2 photon per pulse. This is per given mu, probability of getting 3 photon per pulse. That can be calculated using Poissonian distribution. As I told, laser follows Poissonian distribution. And Y2, Y3, they are called yield, means they are like conditional probabilities. Suppose Alice sends 2 photon and Bob measures 2, given Alice sends 2 photon. Okay, 2 photon state. So that same way 3 photon. Okay, Bob measures 3, given Alice sends 3. So that's a conditional probability. And then using this, you can calculate like theoretical values for different mean photon number per pulse and experimental values. They are matching pretty well. So, and then we have like found out the secure key rate. You see that now you are including, instead of just single photon, you are including 2 photon and 3 photon terms, and this is like error correction efficiency of error correction efficiency. How efficiently you can correct the errors, this factor tells. And this is like binary standard entropy, and this is like error rate. Okay, here all these are error rates. Okay, E mu is also error rate. This is also error rate. So you get higher key rate. You can see that for a CD protocol, you get much higher key rate compared to this is DCAR or BBT4, and this is for CD protocol. So that's what you get. And you can go for 2.2 up to mean photon number per pulse. You can go up to 2.2 when you're using coincidence detection protocol. And you can have a much high key rate. And you can define like security parameters also. Like when you're using prepare and measure protocol, basically you have a mean photon number per pulse and transmittivity. These are the two things which may fluctuate. So depending on their fluctuations, like you can set for your channel 1% or 2%. So we have fixed 1% fluctuation for mean photon number per pulse, as well as for transmittivity. And using that, one can calculate like fluctuation in coincidence count, okay, and total coincidence count. So you can derive this parameter. And same way you can do like coincidence, total coincidence count and singles counts, you can derive this parameter. So Chi and Zeta. So you can derive these parameters. And if they are like within bounds, so you can say it's secure. That's what we have done. You can check that this is mean photon number per pulse, mu, and these are the coincidence counts. Like one is like theoretical, one is experimental. So they are within the limits. Okay, you can say this fluctuation. Yeah, you can see that it's much below the theoretical value for 1% fluctuation in mu and eta transmittivity and mean photon number per pulse. So that's what you do. And then you get like, you can see that for coincidence detection protocol we have done in the field also, you get much higher key rate. Okay, let's go to entanglement based quantum protocol. So before you go for entanglement based quantum, please let me know the time when I have to stop. I will stop there, then we can have discussion. Okay, it's so let's
What? 5 more minutes, sir.
5 more minutes. Okay.
5.
I think I will take 10 minutes. You will have to excuse me. Okay. So before we go for this entanglement based quantum key distribution protocol, we have to produce entangled photon. Okay. So I already have explained you. So this SPDC, we call it spontaneous parametric down conversion. This follows energy conservation and momentum conservation. Okay, momentum conservation, you can see that Kp, this is momentum or wave vector for pump photon, and this Ks and Ki, this is down conversion. You call signal and idler. I is idler, signal. These down convert photons are called signal and idler. This is wave vector for down converted photon, Ks, Ki. And so you see that this energy conservation also, you can see omega p is equal to omega plus omega. Okay. So this is the diagram or setup to produce entangled photons. You have a pump 405, and this is pump. This is nonlinear crystal we are using, Chi2 nonlinear crystal. This is PPKTP crystal. You have to maintain it certain temperature, okay, to get these photons. So this is D means dual. You can use for 405 as well as 810 nanometer. So, and this dual means this half wave plate works at both the wavelengths like 405 and 810. So when we say 405 and both the photons are 810. This is called degenerate down conversion. You can have non-degenerate also, but here we are using degenerate. Both are having the same wavelengths. And once we have generated these photon pairs, entangled photon pairs, we can measure correlation correlation. And since we are measuring correlation, you get this kind of fringes. Like in interference, we measure field correlation and we get fringes. Same way here we are measuring correlation correlation, we are getting this interference fringes. And we can calculate the visibility of these fringes, and its visibility is more than 70%. Are using the visibility, we can find out the Bell parameter, and Bell parameter is indicator that your photons are entangled or not. If it is more than 2, you can say that your photons are entangled. So we are getting 2.63 plus minus 0.02. So our photons are entangled. Its maximum value is bounded by 2.8 to 2 root 2. Then you can do the quantum state tomography. State tomography is like the CT scan coherence. So you same way tomography, that is also tomography. So you take you reconstruct the object which we are taking image. So same way you can have number of measurements and reconstruct the state here. So that's called quantum state tomography. And using quantum state tomography, you can tell whether you are getting the state which you wanted to generate. So we are getting the state which we wanted to generate very close, 0.975. This is the fidelity. And this entangled photon source, we are planning to take it to space and to check whether it's working fine in space. So maybe within a few months, it will be there in space. So that's how you measure the Bell parameter. As I told, Bell parameter is very important to verify whether your photons which you have generated, they are entangled or not. So you do the coincidence measurement. Coincidence measurement means always I am emphasizing that is at the heart of quantum mechanical measurement. So you measure the coincidence measurement. And these are the angles of polarizer and analyzer. You fix the angle, means this is one angle, then 90 plus, okay, you add. So at different angles of polarizer analyzer, you fix and then measure the coincidences, and measuring correlation coefficient, you plug in here and you get the Bell parameter. So that's what this is BBM 92 protocol, which is very similar to BB84, but we are using entangled photons. So here it's not prepare and measure, it's entangled photon, 2 photons. 1 photon goes here, 1 photon goes to Bob, 1 photon goes to LS, and randomly you select the basis. Okay, again, horizontal, vertical, diagonal, anti-diagonal. You can see that if they are using the same basis, they will get the key. Okay, you see here. But here there is error. They are same basis they have selected, but you see this is diagonal, this is anti-diagonal, so that's the error. So you get finally this key. Okay, it's similar to BB84, except you are using entangled photons. And same way, like you are sending these 2 photons, then measuring here, just prepare and measure. Here you have entangled photons, okay, source, and one is going to Alice, one is going to Bob. Again, you use 4 detectors to measure 4 correlation states, okay, and then you take the timestamps. And this is like, you will notice that now this Alice and Bob, they are sitting in the same cabin. So distance is different from 200 meters, and that will be reflected in your delay. So that's what we have done, 200 meters as well as 35 meters we have done. And this is entangled photon source going to Alice, one going to Alice, another going to Bob. This is much more like larger version, and these are the cabins. Okay, this is the reflector. So we have measured for 200 meters, okay, and we have observed that our photons remains entangled even at 200 meters. Okay, we are getting Bell parameters 2.54, and this is like a theoretical fit. Okay, middle line, and this top and below line, this is 98% confidence interval lines. Okay, so what we do, you fix like H. One polarizer you fix at S, then you rotate the other polarizer, and that's how you get this visibility curve. Same way you fix D and then rotate the other polarizer, and you can fix all these upward and then keep on rotating the other. That's what you get. So So here, as I told, distance is slightly less than 200 meters because we have brought both in same cabin. So you see this delay has changed now. And because we are generating HS plus PV state, entangled state, so if you're sending H, we will get H maximum at this much of delay. Any slightly difference, like say 648.5 nanosecond, we will not get this kind of counts. So this HH plus PV, because you are generating, so you just count these numbers and that will give you the key, okay, key rate. This is shifted key rate. And then you can calculate beta error rate. This is 4%. Well within, like for BB84, like BBM92 also will have same error threshold 11%. So that's what our transmittivity of the channel is 0.70. So we have done for 35 meter and 200 meters. You can see that, and we have observed that atmosphere plays a great role in like key rate. Okay, you can see that our key rate follow the atmospheric parameters. Okay, so if we are using a satellite-based quantum key distribution, by measuring the key rate, you can derive the atmospheric parameters as well. Okay, that's the beauty. So you can have two things at the same time, atmospheric parameters as well as key distribution. So we have done free space, but as I told in the beginning itself, one has to connect free space to fiber. That's what we are doing presently with CDOT, okay, Center for Department of Telematics, okay, so government organization. So that's what we are working, how to integrate fiber with free space. So that's what this is C dot BOC PRL Alice. So both are measuring, both are generating K1, K2. This is K1, this is K2. So you do XOR and then K1, K2, send it to here, then again XOR and send to here, again XOR, you can get the same. And you can do the communication. That's what we're doing. So this is the DSC project on which...
please, a little bit in a hurry.
Yeah, I will just finish. Don't worry. Just 2-3 minutes. Yeah, just don't. So these are the this is the work done under the project Free Space Quantum Communication Road to Satellite Quantum Communication that was given by Department of Science and Technology. Under that project, we have generated entangled photons. So all those things I've talked about anyway. So that's what is the progress. The second phase, we wanted to have like a portable ground stations and for longer distances, more than 10 kilometers and probably per satellite. But second phase of funding still has not come. So we have completed first phase for 200 meters. That's what we're supposed to do. And you might be aware China has launched missile satellite and China has taken a lead, okay, in this quantum communication. They have demonstrated more than 1200 kilometers of entanglement distribution and have used for this entangled photons for making quantum key. They have used, like they have done BB84 also for 7600 kilometers secure quantum communication, video conferencing, intercontinental, Beijing and Vienna. You can see that 7600 kilometers they have already demonstrated. China, like they have done teleportation, uplink, downlink, everything they have done. So they have taken a lead, and in fact, all these major investment from all the countries all over the world has started pouring in quantum technology because of this missile satellite launch and their results. Okay, so it's not only China. Italy has also done that. Rather, they were the first to report this feasibility of quantum key distribution using satellite. And Japan has also done. They launched much before China, but published results quite late. Okay, they have very compact ground station, very compact payload. They could do this B92 protocol. And Germany has also done long back 13 using aircraft for 20 kilometers. Okay, this quantum key distribution, prepare and measure. And that's what we are working on. We are developing payload for quantum key distribution. This is 84, and this can be replaced with entangled photon source. Okay, and when you are using entangled photon along with BB84, you have to have like 2 telescopes. Okay, and this RF communication is being used for this classical communication when you are using satellite. So same way, this is detection. These are the detectors. Okay, 4 detectors and, at ground station. And receiving aperture, like receiving telescope, has to be larger, because when it comes to the ground, beam becomes like larger, divergence, because of natural divergence. So it has to be larger telescope compared to what we have in the satellite. You can have 10 to 20 centimeter telescope in satellite, but at the ground you have to have 1 meter around. So that's what this is the future plan of work at Quantum Science and Technology program at PRL, effect of turbulence. That's what we are trying to understand, and how to mitigate it for terrestrial as well as satellite-based quantum key distribution, simulating conditions for uplink and downlink, and then development of device-enabled quantum key. That is very important. Okay, as I talked of the side channel leakage, so device-enabled quantum key distribution is very important. Then entanglement swapping and quantum teleportation in phase space towards quantum communication network. Without this quantum communication network, there is no point of talking of quantum key distribution, because it has to be like in global network. Then only it is feasible, it's practical. Otherwise, just 2 points secure communication doesn't make much sense. Then you can use like structured beams to make more robust and secure key distribution. And then photonic quantum computing, that may be the best bet for worldwide quantum web, because you can seamlessly integrate like communication and computing. So with that, thank you for your patience and listen.